Hello, Sarthak, can you hear me?
Yes, sir.
Sarthak, you should remind me. I will write the letter. Can you see
Yes,
the screen?
yes, sir. Yes, sir.
Can you hear me? Hello?
Yes, sir.
Hello? Can you hear me?
Yes, sir.
Okay, I'm just starting. I'm giving you the background again. Ascoli-Archilate theorem. Next is a topological space and Cx, the linear space of all real valued continuous functions. On X, that's CBX can prove this way because in this case X is compact, Cx will be contained in this. You don't need to go to R to the power X. But this BXT that we have proved last semester is complete. So if you take a Cauchy sequence here, then this will be Cauchy in Bx. Bx is complete. So there exists f belongs to Bx such that Fn goes to f in Bx. But here we use the result. This means uniform convergence. But we have done that uniformly convergent limit of a sequence of continuous function is continuous. By using this result, f is continuous. Because f belongs to Cx. That means you get this. Every Cauchy sequence here converges to a function. Okay, you need that result. Uniformly convergent limit of a sequence of continuous function again is continuous. So Cxt is complete. because in my book I have given Ascoli-Arjula theorem. That again I have reposted the note. Ascoli-Arjula theorem. Last semester also I did. Again I did. So you remember that. Okay. So that here, look. So that if X is compact, I put then CXT is a complete metric space. Now you see that if you have a complete metric space, separately don't confuse with this X. Suppose you have a complete metric space. Separately I am discussing this. Complete metric space and okay. Suppose you have and A subset of X. Now you see that A is total, if A is totally bounded, A is totally bounded implies this is general result. A bar is totally bounded in X3. But X3 is complete given and A bar is closed. So A bar T is also complete. Since X3 is complete. So we are getting A bar totally bounded and complete. We have done that result. A metric space is compact if and only if it is complete and totally bounded. So that you get A bar is compact. Okay. So actually A bar is compact. Okay. So you actually will be getting this. Now look on the reverse side, if A bar is compact, then it will totally bounded. Subset of a totally bounded set is totally bounded. Okay, so that A will be totally bounded. That means what we are proving here? That proved here that A is totally bounded in X T if and only if a bar closure of A in X, a bar is compact in X. Okay, look, A need not be closed. So why we are doing this? Because we are going to state a little more general statement of that Ascoli-Arjula theorem. So Ascoli-Arjula theorem, and remember that I already said now X compact CXT you are taking. Remember that actually this is a Banach space. This infinity norm gives you this metric. Often we write this to indicate this is a topology given by this metric. Okay, right? So that this is a complete metric space. Actually, it's a Banach space. Now, if we go for a compact subsets, Ascoli-Arjula theorem gives characterization of compact subsets of this. Let's see. A compact subset in a Hausdorff space will be have to be closed. So suppose you do not assume closed. That means suppose you take this. By the previous observation, what I will say that A says totally bounded in CX T if and only if his bar is compact in CXT. Usually Ascoli-Argela theorem only gives the characterizations of this compactness. So but because of this I need to characterize basically totally bounded subsets in CXT, the characterization. So Ascoli-Argela theorem general version will be characterization of totally bounded subsets. So that means you'll get characterizations totally bounded sets in CXT. Now you should not confused. Look, here bounded in CXT, symmetric space. That I last time explained. Bounded in CX actually means uniformly bounded. Bounded means actually uniformly bounded. Remember, uniformly bounded means what? If you take this, was non-empty set you take. S is called uniformly bounded if there exists m greater than 0 such that, look, yes, for all f belongs to S and for all x belongs to x. But this means you f infinity. That means f infinity is less than equal to m for all f belongs to S. But this precisely says it is bounded. So uniformly bounded, don't forget. That is means actually bounded. Okay. So uniformly bounded means bounded. Actually, analysts they prefer to use this term, particularly the PDE people, that uniformly bounded. Okay, so that uniformly bounded means actually bounded in this. But totally bounded, you have seen that it is stronger condition than bounded. Totally bounded in metric space, like discrete metric space. It is bounded, but it is not totally bounded if it is infinite. Totally bounded implies bounded, not the other way. So that means totally bounded here and uniformly bounded, they are different. Okay, right? So I said basically I want to characterize compact subset. Basically, I need to characterize totally bounded subset because this is complete. And so totally bounded implies this, but it may not be true. Okay, so look how many types of boundedness I am considering here. This is boundedness in CXD means uniformly bounded, totally bounded. Another thing I said yesterday, point-wise bounded. You should have clear idea about what kind of boundedness you are considering. Point-wise bounded means for each x, suppose S you have this, then S is called point-wise bounded. If given x belongs to x, there exists, this will depend on x. mx greater than 0 such that this for all x this will depend on this. Okay, so this is called pointwise bounded, and I said uniform boundedness implies pointwise boundedness. Uniformly bounded implies but again here this signal is not true. Okay. So totally bounded means uniformly bounded here. Okay, this is uniformly bounded. This implies pointwise bounded. But none is reversible. Totally bounded implies bounded, which means uniformly bounded implies pointwise bounded. Okay, right? So now I can state, look at my book and that, what I am saying this. Okay, this theorem, Ascoli-Argela theorem, this chance statement I'm giving. Look here, I'm taking a compact Hausdorff space. That usually it takes space to be Hausdorff and that, because compact Hausdorff space will be the T4 space. Because I want to ensure that I mentioned that we have enough of good continuous function, non-constant continuous functions. So if we just take compact space, it may not have that. But if you add compact Hausdorff, it will give you T4 space. So it will be a Tychonoff space. So you'll have enough of non-constant continuous function. So you take X compact Hausdorff space. But whatever discussion I had before, that is valid for any compact set, compact space, compact Hausdorff space. I'm just giving the hypothesis in that. Okay, and S is a non-empty subset of Cx. This here, the equicontinuity will play a role. So you should understand the concept of equicontinuity very well. So the following are equivalent. So look, here you see that. I said totally bounded implies uniformly bounded implies pointwise bounded. But if you have the equicontinuity present of S, then they are all same. That means A following are equivalent. S is totally bounded this is the metric space. B. S is uniformly bounded. S is uniformly bounded means bounded in that I explained that already. Uniformly bounded in there means bounded in CXT, but totally bounded implies bounded, but bounded may not imply. But here, if you have this and equicontinuous. Okay. C. S is pointwise bounded. And equicontinuous. In fact, continuous I have given the definition pointwise bounded, and if you are totally bounded, A implies B. Note that any totally bounded subset is bounded. If S is totally bounded, is uniformly bounded. And totally bounded implies equicontinuity. This we can prove. Okay, that I've given the proof. Okay, right. But before that, that means I'm going to explain our proof. Now look, that means if you take equicontinuous here, in addition, if you assume equicontinuous here, that means all these will be equal. That means this will be totally bounded, uniformly bounded, pointwise bounded. It will be the same thing. Okay, right? Because you are putting equicontinuity before them. Okay, so that all these things will be. That means when if you take equicontinuous, that is the importance of it. If you take X to be already equicontinuous, then all these concepts, totally bounded, uniformly bounded, pointwise bounded, will be all same. Okay, so that is the case. Now let us prove this, that how we are proving this. Now look, A implies B. I said totally bounded and uniformly. Uniformly bounded means bounded here, so it follows. But you'll have to show that S is totally bounded implies this is equicontinuous. Look how much that I'll have to show. And look, B implies C is immediate because I already explained that if it is uniformly bounded, it will be pointwise bounded. It will be, if it is uniformly bounded, it will be pointwise bounded. And it is equicontinuous given there. So B implies C is immediate. So B implies C immediate. So that this I need to prove, and I need to prove C implies A. Okay. So that S is totally bounded. Okay, but equicontinuous, let me tell you that. This actually I proved last semester. You can prove that yourself, or you can look here. So I am going for C implies E. That if it is pointwise bounded and equicontinuous, then it is totally bounded. Okay. So I am going to prove this thing. C implies A. Okay, this is, you could read yourself, do it. It is simple. But for before that, let me again recall what is the definition of equicontinuity. Which is, first of all, we define equicontinuity at a point. About totally bounded, why it should be equicontinuous, that I am going to explain to you, so that you can understand the proof. That equicontinuity at a point x belongs to x. And if it is equicontinuous at all the points of x, then it is called equicontinuous. Equicontinuous at a point x to x, which is real valued function, I told you. So that it means that given epsilon greater than 0, there exists a neighborhood u of x. Yep, I have taken v. You can take this v if you want. There exists a neighborhood v of x in x tau. For that, you don't need compactness. This is just definition of equicontinuity, such that fy minus fx less than epsilon for all y, of course, belongs to v. Okay. And since I'm talking about equicontinuity, that means for each function here, that means and for all f belongs to s. That means same neighborhood is working for, because of the continuity for a given a point for a single function, you will always get it. Okay, right? But here I'm saying the definition, this is for all f, single neighborhood is working. That means that's why it is called equi. Now look, if I have s only finite, suppose I have this, then correspondingly for each point, for each function you will get, suppose you get vi corresponding to fi. Then look, V intersection Vi, I 1 to n will be again a neighborhood of X, and that will work. So if S is finite, it is always equicontinuous. Okay, so that when we consider actually equicontinuous family, it makes sense that if we it becomes makes sense if we consider infinite family. So usually we consider infinite family, but totally boundedness, again I'm telling you, totally bounded is in a matrix is very close to compactness. It is only the closed thing is missing. So that equicontinuous, again look here the finiteness is involved. By totally bounded, if we assume totally bounded, from this we shift to a finite family. By the definition of totally bounded. And here I get the neighborhood, that neighborhood works. Okay, that's the role played by totally boundedness, total boundedness. That you should understand. Okay, so that exactly I have done that. Okay, here ball of that, because it's a metric space, I have taken this. This is ball centered at F with radius, open ball with radius epsilon. Okay, right. So this is so, but that's why I want to prove C implies A. So A implies B, you can prove that. Okay. In fact, totally bounded implies equicontinuous. I do not need X to be compact. It is for any topological space will work. Okay, compact. Sorry, as long as actually, if you take this, look what I'm saying. If you take this CBX, okay, then you can prove that. So this metric is defined here. So S is if S is totally bounded in CBXT bounded continuous functions, then S is equicontinuous. That's the proof actually says. Actually, you do not need X compact as long as you consider X compact gives me Cx equal to CBX. Okay. Now C implies the come here. C implies A. Okay. Here C you have what is C? C means S is pointwise bounded plus equicontinuous. Okay, and A is this is totally bounded. Pointwise bounded is much weaker than pointwise bounded because the pointwise bounded weaker than uniformly bounded and uniformly bounded weaker than totally bounded. So actually it is 2 steps weaker than totally bounded. But if you have equicontinuous, they will be same. Okay, right? Now look what I am doing. So I need to prove that, I need to show. And this is given. Okay, so totally bounded means definition, you remember that. What is totally bounded? The metric space in that. If you have a subset of X, then A is called totally bounded. Recall the definition. If given R, that means for all R. there exist finitely many points. There exist x1, xn in A. It doesn't matter, you can choose them in A as well as in X. That can be shown that such that yeah, you should understand these points, the number of points n will depend on R, and the points itself will they themselves will depend on R. So it is not a fixed set of points, that finite set. All you can rhetorical write there exists a finite subset of A such that you can write this way if you want. That's the proof. Hmm. There exists a finite subset FR, because to indicate this will depend on this of A such that yeah, basically this given R greater than 0 there exists a finite subset FR of A. Some people take X but it doesn't matter. Then I can prove that I will have the points up there. By expanding the radius, I can have that. So this is totally bounded. So I'll have to show that totally, but that means I'll have to start with any R. Sorry. So that choose any R greater than 0. I have taken epsilon. Choose epsilon greater than 0. Okay. Now look. Here I have equicontinuity. So S is equicontinuous. Okay, right? Choose epsilon greater than 0 and then take any x belongs to x. Okay, arbitrary x. But S is equicontinuous, so equicontinuous at x, so that there exists a neighborhood Vx. Vx. There exists a neighborhood Vx of x in x tau. This is I've taken compact house fifths such that we have this. Is then epsilon for all f belongs to S and for all y belongs to Vx. Okay, so that we are getting this. So now I do it for all x. Okay, so Vx is the neighborhood of x. Neighborhood of x means open neighborhood of x. So that you are taking. Now take so that I have this. This is my index set also. Okay, right? Got it? Now look where I'm using. In the beginning, I have given that x to be compact. In fact, I have given a counter example that remark that if x is not compact, then it need not be true. Okay, so x is this. It's an open cover, so that means Vx, x belongs to x, is an open cover of x. Okay, but x is compact. X is compact. So there exists x1, x2, xm. I've taken in x. So there exists such that Look, I have got hold of finitely many neighborhoods in this. Okay, right? And already about equicontinuity, you will get that thing for each Vxi. Remember the condition in that. Okay. Now look. So I have used equicontinuity. But remember that, see, I had equicontinuity plus pointwise bounded. Okay. So that here you see that for each point fxi, f belongs to S. I have taken the point xi, one point at a time, and this all f. I have given hypothesis the S is pointwise bounded. That means this is bounded. Pointwise bounded means actually what? It will be bounded subset in R. So this is bounded for each this collection. Okay, right? In fact, I can take them with to be uniformly bounded also in a sense, because I can choose only finitely many bounds you'll get. Okay, is bounded. Hence, now take K, define K. Look, this actually I need to. What I am doing K? K, you are taking this. Look, don't confuse that. Each fxi is in R. Leg is paining. Fxi belongs to R. So I have taken 1 to M. So M tuple. So that means it belongs to R to the power n. So that means this is subset of R to the power n. First of all. Okay. And this is bounded. Look, when you got R square, R cube, R gen, what actually bounded subset will mean? It should be contained in a ball, but at the same time, if it is contained in a parallelepiped, okay, balls, that will be bounded. That means for, look, in R2, it will be bounded if and only if it is contained in a rectangle, right? Okay. So that here, that means each coordinates, the component coordinates are bounded, then it will be bounded. Look, this is bounded. Okay, so suppose this is bounded, so that means suppose this is contained in A1, B1. Okay, is bounded in R. Similarly, this is bounded in this. That means K will be contained in this thing. Okay, but this is a bounded set in Rm, so K is bounded. Okay, got it? So K is bounded. Okay. Now I'm saying in usually bounded set need not be totally bounded, but in Rm, that also you should observe that any bounded set is totally bounded because K bar, okay, it will be closed. Closure by bounded set is bounded. It is closed and bounded in. I'm explaining what I've written here in Rm. But Hein-Bodel theorem, look here, Ascoli-Argela theorem. I said this analog of Hein-Bodel theorem for this function space, but I am also using Hein-Bodel theorem. It's closed and bounded in Rm, so that by Hein-Bodel theorem it is compact, but any compact set is totally bounded. So K bar is totally bounded. A subset of a totally bounded set is bounded. So that in Rm actually every bounded set is also totally bounded. So that means in Rm there is no difference between bounded and totally bounded because of Heinz-Borel theorem. This you should know. I'm writing here because of Heinz-Borel theorem. I'm writing HP. In Rm, there is no difference between bounded subsets and totally bounded subsets of R. Rm. That is, if you take this, okay, this should, so I am using that fact, okay, so that K, by Heinz-Borel theorem, K is totally bounded, that thing. Now, K is totally bounded, K is this set, remember that. Okay, so that you get this thing for given epsilon that you have chosen. Here the points are this, that is finitely many points you will get. Okay, that's why Fj. Look here, look. Okay, I'm not changing this, so the function is changing. Okay, so these are the points I have got because of the compactness of the space X. Okay, so remember that these points are fixed. क्या हो रहा है? Now, so this point is fixed. This is okay. This is a subset of X. Only here variable is F. Okay. Now look, so that is totally bounded in R to the power M. Okay. Got it. So that we'll get that epsilon. Given epsilon, you will get finitely many balls in R to the power M, which will contain K, which will contain K. But the balls will depend on this, so that there exists. So K is totally bounded, hence there exists F1, Fn. That's why there I have 2km. This is different. There exists in S, because this is the collection. Okay, so finitely many F you will get from here, which will cover the corresponding balls will cover. such that you have this K. Look here what I'm writing. Fj, I'm writing. This is the point there. Okay. And epsilon is the radius. That's the ball. And finitely many points. So J 1 to N. Okay. Right. This concept wise it is simple, but only it is more painful to write properly. That's why I'm writing properly. Okay, Fj J1 to M. Okay, so you will get finitely many. Okay, that you got. Open ball in Rm with respect to usual is distance metric rho. We have called it rho. That's fine. Okay, this metric I'm taking that I have called rho. Okay, you claim that S is this. Remember, this was the original thing. We were given pointwise bounded and equicontinuous. You needed to prove it is totally bounded. And this thing I am going to show that claim. 4 epsilon I am taking. This is this. Okay. This is the claim. Look, epsilon greater than 0 I got. If you want exactly epsilon, then starting with epsilon, you start all this computation, you do for epsilon by 4. Then you will end up with epsilon here. Okay, so it's not a problem. Okay, that is the claim you do, and that is exactly the epsilon was arbitrarily chosen. And I have produced a finitely many f's such that it is contained in that. So S is totally bounded. This claim I am not proving for you. You look at the note. Okay, look at my book. You will get it. It is very simple thing now. I have I have proved the talked about, clarified everything. The difficult part. This is simple inequality on that. Okay. In fact, you can see that. Okay. But look here, this thing you'll have to use this thing. That's why you will get this. Any x will belong to some vxi. So this will come that. Okay. That exactly vxi it will come. Okay. So that this I'm leaving it to you. Make sure that you do it. Exercise. Okay, so I'm coming back after 5 minutes. I will talk about the remark. I will talk about. So this is the proof I have given. Basically, I have given the complete proof. This is simple 2 lines. You should make sure that you do it. My leg is paining actually. Okay, I will come back after 5 minutes. Hello, now listen. So that I have given the proof. Look, the proof, you can look at Lalipanthi's and look at my proof. It's very straight. I have used compactness straight. I didn't go for any sequential characterization of compactness. Okay, so that here I put this. Compactness of X is necessary in Ascoli-Arjela theorem. In fact, look at that. Even if you take C star, here as I told you, the topology is to the right for this bounded function. So for analyst, it will be the notation this. Okay. And if you take this, each fn for n, for each n, you're defining r. X is r here. You are defining x. Yes. This is so fn. You should check that. Pointwise bounded is not a problem. That I have given that. Is pointwise bounded and equicontinuous. But I said you have the difference between this n not equal to m. Okay, you have that. So that, well, so Fn, this implies this is not totally bounded. Okay. So n equal to 1, it will come. So that 1 minus c and that. Oh, sorry, this I got. Greater than equal to. So if you choose epsilon, this. For that epsilon, you won't have it. Okay, right? It won't satisfy the conditions of the total bounded. So it is not totally bounded. It is happening because you know the R is not compact. Actually, the next corollary is often referred to as Ascoli-Arjela theorem. That I already told you that X is compact, so that if you take this, Cx is compact, of course, and then S is compact. In Cxt, if and only if S is closed and bounded in Cxt. Look here, I should point out, you should understand and okay, continues. I have been careful to write, look, closed boundedness, it is a subset of Cx. This depends on the metric of D, metric D, big D of Cx, whereas equicontinuity only depends on the topology of X. It doesn't depend on this. Equicontinuity is not related to this here. Okay, equicontinuity depends on that, so I have written separately that it is closed and bounded in CXT and equicontinuous. Okay, so this is the usually people use it. Okay, that means closed, bounded, and equicontinuous will be ensure compactness. I already said in a metric space, if you have closed and bounded, it need not be compact. That means discrete space. If you take infinite discrete space, okay, right? That is closed, bounded, but it is not compact. Okay, In fact, any infinite subset of an infinite discrete space, you can see that will be closed and bounded, but won't be compact. Okay, so that here the gap that you should know that AS is compact if and only if closed, bounded, plus equivalent. This thing you have. Okay, so the gap is here. Compact subset will be always closed and bounded, but unless you have equicontinuity in CXT where X is compact, it won't be compact. Okay, right? So that let me tell you that I'm not going to give you the proof of Ali-Francis-Perkins. I'm going to explain that proof, that just how he proved that. Okay. Well, I think you read first, then I'll. But before that, I want to talk about Stern-Weierstrass theorem, approximation theorem. Okay, I'll talk about. Well, Monday I will finish this. Coming Monday I will take the class, and then next week I won't take any more class. Okay, so Monday is at 14th March, I think. Yeah, March 14 I will take the class. After that it will be March 21. Okay. So after this function space I did, I will talk a little Tychonoff product theorem. And then I will go to connectedness. I taught a little bit of connectedness here. I plan to teach in detail as much as time permits. Okay. Tychonoff product theorem, probably one day I will need that. Okay. Now look here. About what about Stern-Weierstrass? I am not going to give you the proof anything else. I just want to talk about Stern-Weierstrass theorem. That what is there. Okay. Thing is, if you take compact metric space, then CXT, this uniform metric is done. X is compact metric space. Take that. Compact space actually. You can take Hausdorff if you want. Okay. What is the idea of that? Look, in topology, when you are handling, particularly the analysis related, that any space you have that, first thing it will be compact subsets of that. If it is not itself compact, to find out compact subsets. So in Ascoli-Argela theorem, actually, for a compact space, don't confuse with this thing. For CXD, we characterized compact subsets, Ascoli-Argela theorem. Characterized compact subsets. This is very important for both for topologist and analyst. But another thing will come. What will be the nice dense subsets of this? Nice, that very subjective. It depends on what you think nice. Nice dense subsets of CX. Well, if it is separable, that will be the. If it is separable, that means we will have a countable dense subset. If it is separable, it's great, it's good. But if it is not separable, next thing you will find out. Look, separation means separable dense subset means what actually? Okay, let me. Why it is not working? Why the pen is not working? Why this pen is not working? I don't understand. Wait a minute. Why my pen is not working? I'm not very sure. I'm going to able to take class on Monday also. Wait, just wait a bit. Suddenly I see that. Well, I think it is not working. Okay, so while I have to say that I don't know what's wrong with my pen. Well, let me tell you that. I'll figure out. I will take the class next Monday, but before that, Stonebuster's approximation theorem, read from my note and read from, let me tell you that we have here, you read from Aliprantis Birkinshaw, page, ये तो बहुत ही problem होगा. This is bit nonsense. चलो पता नहीं क्या हो गया. It's not working at all. Okay, I will take the class on Monday on that. I don't know why my pen is not working. But it will write about the nice dense subsets that when actually particularly they will be separable. Okay, so that's the crux of Stone-Weierstrass approximation theorem. So I will take the class Monday. By the time I will fix out my pen. Fix up pen. Okay, okay, see you, bye. देखा ही तो अच्छा ना.